September 17th, 2025. NASA's Chandra telescope confirms the impossible. Astronomers have just discovered a black hole that's growing at 2.4 times the maximum speed physics says is possible. J1144 weighs in at over 1 billion times the mass of our Sun. Yet it was already this massive just 920 million years after the Big Bang, shredding the most fundamental rule in astrophysics. If even the universe's speed limit can break, every simulation and textbook on cosmic origins is on the line tonight. So how can something this colossal defy the laws of physics, and what else might be waiting for us out there? To understand why this changes everything, we first have to know the rule it shattered. Gravity is the universe's master architect. It pulls gas, dust, and even light itself toward the center of a black hole. But there's another force at play, one that pushes back. As matter spirals into a black hole, it heats up and emits a flood of energy, mostly as high-energy light. This outpouring of photons creates a pressure, an outward push that fights against gravity's pull. Imagine trying to pour sand into a funnel, while a powerful fan blows upward from the bottom. Gravity is the hand tipping the sand in. Radiation pressure is the fan pushing grains back out. This cosmic tug-of-war sets a limit. If the black hole shines too brightly, the radiation pressure grows so strong that it blows away the very gas trying to fall in. That limit is called the Eddington Limit, first calculated by Sir Arthur Eddington in 1918. It's the theoretical maximum. Beyond this, the black hole's own light should slam the door on further growth. For a billion solar mass black hole, the Eddington Limit means swallowing about 3,000 suns worth of material each year, but never more. The equation looks simple enough. 4 pi times gravity times the black hole's mass times the speed of light divided by the opacity of the infalling gas. It's a balance point, not just a number, a speed limit for cosmic feeding frenzies. Astrophysicists have relied on this rule for over a century. The Eddington Limit shapes every model of how black holes and galaxies grow, from the first stars to the present day. It draws a line in the sand. Below the limit, growth can continue. Above it, infalling gas is blasted away by the black hole's own brilliance. This is the rule that J1144 just shattered, forcing scientists to question whether gravity and light always play by the same rules, or if something deeper is happening at the edge of physics. Every simulation of the universe, every digital model that tries to predict how galaxies form, merge, and grow, leans on the Eddington Limit as a cornerstone. It is not just a number tucked away in an equation, it is the rule that tells us how fast black holes can eat, and by extension, how quickly the first galaxies can take shape. If you break that rule, the entire script for cosmic evolution starts to unravel. The timing of the first stars, the birth of early galaxies, the pace at which structure spreads across the universe, all of it depends on this cosmic speed limit holding firm. Astrophysicists trust the Eddington cap to keep their models realistic. They feed it into supercomputers, setting the boundary for how much mass a black hole can gain in a year, a million years, a billion. Without it, predictions about the brightness of quasars, the growth of galactic cores, even the chemical fingerprints we find in ancient starlight, all become guesses on shaky ground. The Eddington Limit does not just shape the story of black holes, it sets the pace for everything that follows, the way galaxies cluster, the temperature of intergalactic gas, the very patterns we see in the cosmic web, stretching across billions of light years. If nature ignores this rule, the consequences ripple outward. A black hole that grows too fast can outshine its entire host galaxy, pouring energy into space and blowing away clouds of gas that might have formed new stars. The balance between creation and destruction, between order and chaos, tips in ways our models cannot predict. The universe starts to look less like a well-oiled machine and more like a wild experiment. That is why the Eddington Limit matters. It is not just a theoretical ceiling, it is the scaffolding holding up our understanding of how the cosmos builds itself. When that scaffolding cracks, every prediction about the early universe is suddenly up for debate. In 2023, a faint X-ray signal from the edge of the observable universe caught the attention of Chandra's control center in Cambridge. The object, catalogued as RACS J0320-35, didn't just flicker, it blazed. Engineers flagged the data, worried that aging detectors or cosmic background noise might be playing tricks. But the numbers refused to budge. Over the next 18 months, every photon was checked, every pipeline recoded. The team ran the data through 3 independent software systems, each time landing on the same answer. This black hole was feeding at 2.4 times the Eddington limit. Not a rounding error, not a calibration slip. The control center called in retired engineers to audit the hardware. Astronomers pulled archival data, matching X-ray readings with radio signals from the Very Large Array and sub-millimeter traces from ALMA. The results lined up. No lensing, no foreground contamination, no hidden trick. Luca Ighina, the lead scientist at the Harvard-Smithsonian Center for Astrophysics, remembers the moment the numbers locked in. It was a bit shocking to see this black hole growing by leaps and bounds. Midnight emails flew between Cambridge and Pasadena. Conference calls ran late into the night. The team's American-built telescope had just uncovered a black hole that shouldn't exist, one that chews through the cosmic speed limit like it isn't even there. On September 17, 2025, NASA and Harvard-Smithsonian released the findings. Peer review had combed through every detail. The verdict was unanimous. The laws of black hole physics had been broken, and the evidence was bulletproof. 1 billion suns swallowed whole, 12.8 billion light-years away, and yet the aftershock lands here, now. RACS J0320-35 is more than just a cosmic outlier. It's a riddle that stretches from the first flicker of starlight to the edge of human understanding. Astrophysicists have spent decades stitching together the story of how black holes and galaxies grew up together, always guided by the Eddington Limit. But this object, seen as it was only 920 million years after the Big Bang, has torn a hole in that script. Luca Ighina, lead author at the Center for Astrophysics, puts it plainly. It was a bit shocking to see this black hole growing by leaps and bounds. The discovery forces a new question. If something this massive can grow so quickly, what else is possible in the early universe? All the models, direct collapse, super Eddington flows, even the wildest simulations, struggle to keep up. Some theories point to slim disks, photon bubble instabilities, or magnetic fields twisting space and time. But none can fully explain a black hole feeding at 2.4 times the supposed cosmic speed limit. Now, every telescope with an eye on the deep sky is joining the hunt. Teams at Stanford, Tokyo, and MIT are combing old X-ray archives for more rule breakers. Proposals for new Chandra and JWST time are stacking up, each one chasing the next impossible object. The textbooks are already out of date. If the universe can build a billion solar mass black hole in its infancy, what else has it managed that we haven't dreamed of yet? The laws of physics are not broken, but they may be wider and stranger than anyone dared imagine. In September 2005, NASA's Chandra X-ray Observatory confirmed that RACS J0320-35 is growing at 2.4 times the Eddington limit, the theoretical maximum long believed to govern black hole growth. With a mass of 1 billion suns and a distance of 12.8 billion light-years, this black hole existed just 920 million years after the Big Bang. These facts, published by the Harvard-Smithsonian Center for Astrophysics, challenge decades of scientific models that depend on the Eddington limit as a cosmic speed cap. Despite multi-year verification and cross-instrument analysis, no current theory fully explains how this rapid growth is possible. Key questions remain. What mechanisms allow such super Eddington accretion? Are other early black holes breaking the same rules? As scientists examine new data and future observatories come online, The discovery of RACS J0320-35 forces a re-evaluation of our understanding of the early universe. For now, the evidence stands. The universe is capable of phenomena that push the boundaries of known physics.